All right, so I'm gonna start by talking about this kind of what really happens when you run your code, and then I'll show you the slides and I'll show you some diagrams, or rather, a single chart that should demonstrate kind of what I'm gonna explain here. So today we're gonna talk about stacks, or just the stack, and we're gonna talk about essentially allocating space in the stack, and also assigning values to bytes in the stack. And this is, as you will see, this is actually necessary for us to be able to convert code from C to MIPS. So when you have code in C, it looks like this. Maybe there's a return data type, or maybe void, and you say, let's start with main. And of course, there's the function body. And here you allocate things, right? For example, you can allocate a variable, and you can allocate an array, my array, give it, 30 elements, 30 integers. And then you can also allocate things outside of this main. And those would be global variables. So you can say int, global var equals to, 100, and int global array. You can do the same thing here, 5, or you can just do what we did before. We didn't give it a number. We just, by number, I mean a size. We just gave it the values of the elements, like 10, 20, 30, 40. And that's going to be a 4-element array that is global. Okay. So the reason why this is a global array is not because I gave it the name global, but because it's outside of all the functions. So maybe there's another function here, say int, add 2 nums, maybe int num1, int num2, and maybe we have some code here. The fact that those two kind of declarations, one for a variable, one for an array, is outside of all the functions that we have, makes them global arrays or global variables. So this is a global variable, and of course this is a global array. So we haven't really worked with global variables and global arrays, but essentially when you create global variables or global arrays, all the functions in your code have access to those global variables or global arrays. So you can access them, you can change them if you want to. Yeah. And global arrays are actually things that we don't like to have. Of course, they're convenient because you can create that variable once outside of the scope of all those functions, and then all your functions have access to this variable. But they're actually bad. They're bad. In almost all cases, they're bad. So you want to avoid using them if you can. So in some cases, maybe you need to. I mean, I know that in some cases you do need to, but in almost all cases, you can actually avoid using them, and it'll be better. All right. So here maybe I can create another variable. I'm just gonna do something that random, and maybe another array. And in this case, I'm gonna actually give it values just like the global array. So maybe 5, 4, 3, 2, 1, 0. So when you hit play, when you hit execute on this code, there's multiple stages that take place. We're going to talk about some of them. We're not going to talk about every single one of them, but we're going to talk about kind of the important ones, and really the ones that we've seen before. So there is this step of converting this code to assembly. So there's a step that takes this C code and converts it to assembly. And we know assembly, right? Assembly would be, branch on equal, add immediate, add, jump, all of that is assembly. And then we convert the assembly to machine code. So machine code would be essentially something that looks like this, which we're going to see in this course. And then this machine code gets loaded into the memory. So do you guys remember the memory? The memory is really what we depicted as a matrix, and we did 8 in most cases. And we said, oh, in those 4 bytes, we're going to put something. In those 8 bytes, we're going to put something. So this is really the memory, which is really the RAM. So once this becomes assembly, and after that, it becomes machine code. Once we have that, we put it in the RAM. And once we put it in the RAM, we kind of organize it in the RAM. And once we organize it in the RAM, we ask the CPU to start fetching and executing instructions. So that's how it works. So the CPU, once we load it, we tell the CPU, hey, my program is somewhere. My program is stored maybe here. Start fetching and start executing instructions. Is that good? Let me get some feedback from you, reactions, like thumbs up or something. Okay. All right. Okay, that's great. So when we convert this C code to assembly and then to machine code, what you may think, maybe you're gonna mistakenly think that this, for example, is gonna allocate space like in the RAM. Like when this becomes machine code, maybe you think that this will become like space, like 4 bytes that contain the number 30. This is really not the case. What happens is when this becomes machine code, this one becomes an instruction that when the CPU runs, it'll allocate space. So this is, the distinction is very, very actually important for you to understand. So let's say we have an array here. When we execute this code, and when this code gets translated to assembly and then to machine code, in the machine code, we're not gonna have 4 byte that contains this, 4 bytes that contain this, 4 bytes that contain this. Essentially, what we're gonna have is code, actual kind of instructions such as add immediate, sub, sub, or branch on equal, that will allocate space either in registers or in the RAM. So that's how it works. So if it's a local variable, so this is a local variable and this is a global variable. So this is a local variable. And let me tell you kind of the summary of how things, whether we go to the RAM or whether we go to the registers. If you have a local variable declaration, then this local variable is going to live. Once you execute the code is going to either put the variable in a register or put the variable, of course, value in the RAM. So 2 options. So if you have a local variable declaration, such as this one or this one, you have 2 options. Of course, you have to choose only one. You cannot do both. You either say, I'm going to create machine code that's going to take this 10 and put it in the RAM, or you're going to say, I'm going to create machine code that's going to take this 10 and put it in a register. Now, I'm not going to tell you yet which one we use, when we use which. So in some cases, you're going to learn that in some cases, when you see this, you're going to say, oh, this one should be in a register. In other cases, you're going to say, oh, this one should actually be in the RAM because of some kind of reason. So we're not going to have this discussion now. We're going to talk about something that doesn't have 2 options, and that's the arrays. If you have a local array declaration, then this one will be translated to code, again, machine code, that will put the values of the array on the RAM, in the RAM or on the RAM. I actually don't know which one is better. Let's say in the RAM. Yeah, in the RAM is certainly better. It's certainly the correct way. Okay. So, for example, here we have an array. In this case, we need to allocate space. We don't have to give it any values. That space gets allocated where? In the RAM. Why is that? Because we have a local array. Even if this array consists of only 2 items, which of course you can put in registers, we don't put them in registers, we put them in the RAM. Same thing for this one. Here, I'm going to have to allocate 6 4-byte chunks because this is an integer. Each one is 4 bytes. And I'm going to put the values, or rather, I'm going to have code. This will be translated to machine code. This is really crucial. That when we execute, that when executed, will put values in the RAM. So this one's going to go to the RAM. Of course, once we execute the code, this one's going to go to the RAM once we execute the code. This one we don't know yet. This one could go to a register or could go to the RAM. Same thing for this one. Now the global variables and global arrays, they go to the RAM immediately. So those actually are not translated to code. Those are translated to space. So this is, again, this is a very important distinction that I want to make sure that you understand. When we convert this to assembly, then to machine code, the machine code for these two will be actually space. So, for example, this one is 4 bytes, and the 4 bytes will be 100. Let's make it simple. Let's say, for example, it's 20. Those 4 bytes that contain the value 20 would look like this: 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, and then we have 16, 8, 4, 2, 1. I think we have another 0 here. Yeah. So this binary is really the value of this variable. And when this gets converted to assembly, then to machine code, that's what you're going to see. You're going to see the bits that contain the value of this one. And same thing for this one. For this one, you're going to have, 4 of those, because each one is 4 bytes. Each one is going to be a value. So 10 is going to be 1010. 20 is going to be 16 and 4. And 30 is going to be, 16 plus 8. We can do it together. 16 plus 8, which is 24. 8, which is 24. And then we need the 4, which is 28. And then we need the 2, which makes it 30. So this would be 30. And then you can have 40 here. So this is very different than what happens here. When this gets converted to machine code, this will be code. This will be zeros and ones, but that will be code instructions that will be executed by the CPU that will allocate space on the RAM. So this one will be translated to space because it's global. This one will be translated to space because it's global. And the arrays, the local arrays, will be translated to code that when executed, will allocate space in the RAM. And the variables here, we kind of don't know, right? The variables could be code that when executed will go to the RAM, or it could be code when executed will go to the registers. So that we kind of, for now, we don't care. All right, let me see if you have any questions. Anybody has any questions? Okay, so let me show you the diagram of where kind of every piece goes. So again, when you run this code, when you execute it, first it'll become assembly, then it'll become machine code, and then it'll be loaded into the RAM. When it's loaded into the RAM, it'll be loaded in a place or space that looks like this. It's essentially a space that contains a kind of fields. The bottom part is called code, and this is really the instructions. So if this one becomes an instruction, let's say for example, let's say we decide to use a register for this one. So that would be add immediate, S0030. This is instruction. And this, of course, is going to have its own machine code. This would go to the code section. So anything that is code, like anything that's code, will be in the code section. Of course, that's going to be in machine code. So it's not going to look like this, but it's going to be like, the zeros and ones corresponding to this. So at some point, we're going to actually talk about converting from this to zeros and ones. That should be an easy part. So that would be the code. The static data is where your global binaries, global bits that we constructed based on the values will live. So all the global variables and the global arrays will be here. Now, if you don't have global arrays and global variables, then you won't have a static data section because you don't have any global stuff, so you're not going to have that. And then there is the stack and the heap, and this is just space. So nothing is going to be in that space. However, as you start executing code, you're going to be allocating space in the stack and in the heap. We're not going to use the heap in this course. We're going to just use the stack. And again, at the beginning, when we load the machine code to the RAM, the stack is going to be empty, but this space will be allocated. The stack and the heap will be empty, but the space will be allocated. So it's almost like a reserved space that your code is allowed to use as we're executing instructions. So that's how you want to think about it. All right, so let's do an example here. And I'm going to use Keynote because it'll be easier to create memory and all of that. All right, let me, and as I do that, you can think of questions, any questions that you can think of. Okay. So I guess that could be my memory. And let's say I have some C code here. And let's say the C code is going to be, let's create some global stuff. So int, global v variable is equal to, 10. And then maybe I'm going to do main. And then I'm going to do, actually, let me also do an array. Int global array is equal to, say 1, 2, 3. And of course, I'm going to do left align like this. And I'm going to change the font to something that I personally like. I know not everyone loves this font, but I like it. And here I'm going to say int is 0 equals to 20. And for now, let's just do this at the beginning, right? So, and then we can add to it and see what happens. So again, there's going to be code, then there's going to be global, and then there's going to be some space for the heap and the stack. So this code is very simple. This one's just going to put, 20 in S0. And let me make this 4. Making it 4 is actually going to be better. Yeah. And we can increase this if we need to. So this is the code section, and I'm going to merge it. And I'm going to say, instead of putting the machine code, because we haven't talked about machine code yet, I'm going to put the instruction in MIPS, add immediate S0020. Okay. Now this is the code. Now there will be kind of more code than just this, but for now we're just going to translate this one. Yeah, I mean we'll do more examples and will be more complete or comprehensive in our translation. But for now, let's just put 20 in as 0, and that's really the code. And that's actually, for the most part, that's it in this case actually. So we're not omitting a lot of details here. And then we have the space that's going to be the global. It's called the static data, right? That's what it's called, static data. And if you read the slides, it says static data is for the variables declared outside of functions. So it's really global stuff. So in this case, you can start with this one or this one. It doesn't really matter. I'm going to actually do it with this one. So I know this is 4 bytes. I'm going to just merge, and I'm going to say global variable, which is 10. So essentially, you're going to put 10 in those 4 bytes. So you're going to put something that looks like this in those 4 bytes. This is 10. Okay. And then you have this array that consists of 3 elements. So that would be kind of 3 rows like that. Let me merge each one. So that would be global array 0, which is in this case 1. And we have global array 1, which is 2. Let me change the values to some other random values, like 7, 9, 1. Oops, that's not what I meant to do. This one's going to be 10. This one's going to be 7. This one's going to be 9. And we're going to have another one. Did I delete it by mistake? Yeah. That's okay. I'm going to say global array 2, which is 1. So all of that, I'm going to change the color of it. All of that is really the static data. This is the static data. This is the text or the code. So I did say text. Text is another name for code. So when someone says the text area, this is really the code. And we have the static data. And then we have here something that we called the heap and the stack. So when you allocate variables on the heap, we're going to start kind of from here and going up. So we go left, then top, left, top. And for the stack, you're going to start here and you're going to go kind of left, bottom. In fact, you're going to start from here. You're going to go to the right and then bottom. So you go kind of 1, 2, 3. So if someone says allocate 2 bytes, you're going to say 1, 2. And then let's say you allocate 2 other bytes, that's going to be these 2. And then you allocate, say, 3 bytes, that would be these bytes. So you keep kind of going down, and the heap keeps going up. And as soon as they touch each other, this is when your program crashes. So essentially you run out of memory. And this is, of course, a kind of a clever way of having two separate entities of using for space. And as soon as those two spaces clash, then you run out of memory. It's not a big problem. You can allocate more memory next time. By default, we allocate some space, but you can increase that. So if your code, if you feel that your code is going to require more space, you can kind of increase the default and rerun your code. Now, as I said, we're not going to be using the heap. We're going to just be using the stack. So you can really ignore that there's a heap. So we don't need to know about the heap for now. All right. Do you have any questions about this? All right. So please, if you have questions, ask me, because I'm going to be asking you questions soon. So if you feel there's something that you need me to explain better, just let me know. All right, so what we're going to do now is I'm going to change that, and I'm going to create an array here. So I'm going to say int local array. I'm going to make it actually similar to what we have here, kind of 3 elements, but I'm going to give it different values, 9, 3, 0. Okay. Now, if you remember what I said a few minutes ago, when you have a local array, where did I say that? Here. If you have a local array declaration, which is really what we have here, this will be translated to machine code. So in your code section, this is the code section. This color is the code section. So this will be translated to code. So it will be translated to code here, that when executed, it will put the values of the array in the stack. Does that clear? This is kind of important because I'm gonna actually again give you kind of a little more information, then ask you questions. So this is what we really should be doing. Okay. So this has to be translated to code that's going to put the stuff on the stack. Now, we talked about registers before, so let me actually erase this one. And let me just, let me actually remove this one for now. And then I can create some space here. I probably would need to, a few more. And let me get rid of 2 of them. And let me get rid of this. I do want to keep some space here just to show you, or rather indicate, that the space that we allocate is not the entire space of the RAM. So there's going to be things that are probably above that space and things that are probably below that space. Okay, let me do no fill here. Okay, so let's see, there's a question here. The question is, if a local array is translated into machine code that adds the information when executed, does that mean that it only exists when the machine code is running? So if by add you mean like populate information, then what then it's not that the yeah, I think let me rephrase your question here for everyone, and then I'll answer it. So the question is, if this becomes machine code, which goes, of course, in the machine code section, in the code section or the text section, does that mean that those values will only be kind of on the stack when we're running the code? The answer is yes, those values will be placed on the stack after we run the code, to be more precise. So after we run the code, so there's going to be code here, and some of it, in this case, probably all of it, because we only have this line, all of this code that we're going to have here is going to allocate, in this case, 12 bytes, and it's going to put those values in those 12 bytes, the 930. And if the question is, does that mean that we only have the values populated after we run the code? The answer is yes. After we execute the code that we have here, we're going to have the values. Now, this is kind of interesting because you may ask, but why? Like, why do we have code that's going to allocate space? Why not just use the space? The reason why we don't use the space from the beginning, such as what we do in global variables and global arrays, is because as soon as we leave this function, the space will be freed. So the thing about the stacks is that every time you go to a function, and of course in a typical program you have many functions, that function is going to use the stack. So it's going to say, okay, allocate 2 bytes. So it's going to go here. It's going to say, okay, I'm going to use those 2 bytes. And then it'll see another piece of code that says allocate 4 bytes. And it'll say, okay, here's 4 bytes. Here's like another, like here we have 2 plus 4. And then there's going to be another piece of code that says allocate 1 byte and says, okay, here's 1 byte. All of that will happen. But as soon as we leave the function, we have to go back to how the stack looked like before we started the function, before we entered the function. So you can think of it as a dynamic space that gets kind of allocated and freed. So as you're running the code, as you're going from function to function, you're going to be seeing a lot of values that are being populated, and then a lot of values that are being freed, and then populated, freed. And this, of course, has a huge advantage. And the advantage is, it allows you to, to use the space efficiently. And as you will see in what I'm going to show you next, the code that allocates those values, in many cases, not in this case particularly, but in many cases, it's actually much smaller than the space that would be allocated. So once we see code of kind of arrays populating, or rather loops populating values of arrays, you're going to see that the code is going to be a few lines, but the space that's going to be allocated is going to be hundreds potentially. So it helps to free that space. So it's good to free that space when we leave the function, because we don't need it anyway. When you leave this function, nobody has access to this except for this function. So when you leave that function, you don't need to have that space in the stack. I mean, nobody has access to it. Nobody should access it anyway. So all right. So let me tell you a few things, and then let me ask you a few questions after that. And I want you to kind of pay attention, because this is not the easiest thing in this course. So this is the space that we have. This is the space for the stack and the heap. Again, for us to start allocating a space or bytes in the stack, we have to start from the highest byte and go down. So if I tell you allocate 2 bytes, it would be these 2 bytes. Now, there is a register. There's a general purpose register that is called stack pointer. So it's a register, just like S0 or S1 or T0 or T1 or even 0. It's called SP. So there is a register. It's called SP, which stands for stack pointer. And this register contains a value. And the value of this register is going to be the first byte that will define the space that's allocated on the stack. I know this is kind of a mouthful, but essentially, let's say, let me give you some examples. Examples are a great way to demonstrate what I'm saying. So let's say I decided to allocate 6 bytes on the stack. That would be those 6 bytes. Now, again, the space that I'm allowed to use is this. This is the space that I'm allowed to use. This is really all that space. However, I decided to only use 6 bytes and put some values in those 6 bytes. The stack pointer, if you did your code right, should be pointing here. In other words, the stack pointer should contain the address of this byte, because this is the first byte in your stack, in the space that you allocated on your stack. Yeah, I mean, that's right, Grace. So when we allocate space on the stack, we start from here and we go left, kind of from left to right. So we start allocating 1, 2, 3, 4. Let's say we allocated 6 bytes. The stack pointer is going to point to here, meaning that it's going to contain the address of this one. And that's essentially going to mean that anything above this byte is something that we're using right now. So it's an indication to other pieces of code that this space should not be used by, other pieces of code. If another piece of code is going to allocate some space, they can go down. It's fine. Let's say there's another piece of code that's going to allocate 2 bytes. No problem. We can go 2 bytes here, and that code can use these 2 bytes. That's okay. But the code cannot use anything above the stack pointer. So the stack pointer is again, it indicates what can be allocated or used. And you never want to allocate or override values above the stack pointer. The stack pointer is the limit. Okay, so the question is, so the stack pointer would likely contain the last value in the stack. Yeah, I mean, whether you call this the last or the first, it's up to you, because this is the smallest. I mean, this is really the smallest value of the stack. I mean, the smallest address. So it could be considered the first. I think I did say the first a few minutes ago. But if you want to say it's the last, it's fine. I really don't think it matters, as long as you know that when we allocate space, we kind of go from here, then we go down. Yeah, and whether you call this one the first or the last, we don't really care. But what you said is important. So what you said is the stack pointer would likely contain the last value. I'm going to even reword it and say the stack pointer should always, every single time, contain this value, which is, again, we can call it the first or the last. Doesn't really matter, but the stack pointer should always point to, I guess, let's say the last value that's been allocated, which is really the first address from the stack, all that space allocated by the stack. Always, it's not going to be likely. It should always be like that. Okay. So let's do an example. So there's a question about the kind of how things are populated in the stack. Let's do an example. I think the example would be the best way to demonstrate that. So here we know that this is going to live on the stack, and the way we do this is first we allocate the space by moving the stack pointer. So when you move the stack pointer, you essentially allocate the space. So we allocate the space by moving the stack pointer, and then we populate the stack with these values. And this is really what I want you to help me with. So I want you to kind of help me translate this to MIPS. It's not very difficult. Let me actually convert that to the same color. Now, the stack pointer right now, when we have no space, when we have no space allocated on the stack pointer is going to be above this element. So this is really the first element or the last element. And I think maybe we should agree on some terminology that'll be easier. But let's call this, the last space in your stack area. And because we don't have any space allocated on my stack yet, the stack pointer is going to be in the byte that's after that. That's kind of right next to that, and that would be here. So this is where the stack pointer is. Because we don't have any space allocated, the stack pointer is actually outside of the stack area. Now, I need to allocate space by moving the stack pointer. So let me ask you this. Can you give me MIPS code that's going to move the stack pointer to a place that's going to indicate allocating 12 bytes? So this is where the stack pointer is. You can add things to it, you can subtract things from it. I'd like to have the stack pointer in a place where it indicates that we've allocated 12 bytes. Let me first ask you, where do you think the stack pointer should be? I'm going to put my mouse here and you can tell me, go down. Okay, all right. So Grace actually gave us an answer. So we can look at that. So the answer is, how about we subtract 12 from the stack pointer? So this is really, I'm going to paste the answer. This is the answer. How about we subtract 12 from the stack pointer? Let's see what's going to happen if we do that. If we subtract 1, we go here. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is actually perfect. This is where the stack pointer is going to be. And I'm going to, guess what I'm going to do? I'm going to just do stack pointer like this, and I'm going to make it point. I think at some point soon we need to stop the recording because this video is getting too long. So this is the stack pointer. The stack pointer is pointing to here. And this is great. This is beautiful. So this means that anything above the stack pointer is going to be things that's important, right? So this is space that I'm currently using. And if there's another piece of code that wants to allocate space on the stack, it would have to be below that. It cannot be above or at the stack pointer. Okay. Now, of course, we did this one. Thanks to Grace. This was done. Now, who wants to help us populate the stack with these values? So I'm going to make this smaller because we do need space here. And I'm going to take this code and I'm going to put it in another text box. So we did the first part. The first part is allocating space. And now I want someone to give me MIPS code that's going to put values here and then here and then here. Now, the question that maybe you have is, do we put the 9 here, or do we put the 0 here, and then the 3 here, and then the 9 here? And for this course, we're going to put the first element here. So this one should be local array 0, which is really... Now, I haven't written code that's going to put the 9 here yet, but I'm telling you what should be there. And as I'm doing that, you can think about the code that's going to put those values in these locations. All right. Okay. What do you think the instruction is going to be? What is the instruction that's going to put something in the RAM? Load word. Okay, that's good. Anthony's saying it must be load word because we know load words, they're going to put words or 4 bytes in the RAM from the CPU to the RAM. So that's good. That's great. And if you remember, load word has this syntax: load word register A, register immediate, and then register B. And the address is going to be the immediate plus the register here. And the value that we're going to be loading into the RAM, essentially putting in the RAM, would be the value that's here. So we know there is something called the stack pointer, which points to here. We know that the value needs to be 9. So what do you think we should do? All right. Not okay, that's that second SP. Okay, all right. So let me actually show you what's the proposed answer. The proposed answer is load word SP 0 SP. Now, when you say load word SP, that means you're going to put the value of SP, which is really the address of this byte, at this location. So you actually got the location right. 0 SP is right because SP, or the stack pointer, is pointing to here. And this is really the address that you're going to put 9 in. It's the address that you would like to put the number 9 in. But this is not 9. This is not 9. This is SP. So you're putting the value of SP in those 4 bytes. Right now it's a mess. What you'd like to do is you'd like to put 9 in this address, at this address. Okay, so Anthony's saying, do we have the address for the array? Well, it's SP. SP is pointing here, and you have SP. You have access to SP. How do we have access to SP? Because we're the one who moved it. I mean, the code decided to move SP by 12 bytes. So the code kind of has access to SP. And SP is pointing at the first address of the array. So you do have the address of the array. It's SP. Okay, I'm going to have to go switch my headphones. I'll be back in 10 seconds. And maybe by then you have an answer. All right. Okay, I'm back. So one other suggestion was to use 156. Now this is bad because first of all, if you use the dollar sign, then you're saying register number. So if you use the dollar sign, you're saying register number 156. Well, clearly we don't have a register that has the number 156. We can only go from 0 to 31. We only have 32 registers. So something that looks like this is clearly not right. I think what Anthony wanted to do is to do something that looks like this, but that's a problem because this is not proper syntax. So maybe what you wanted to do is put this value in a register, maybe T0, and then use T0 here. Now we can do that. Now this value is incorrect, of course, but I'm going to do that anyway. I'm going to say add immediate T00156. Yeah, this is not clear what you're saying here. Okay, let's go back. Let's go back to what we had before. Maybe what we had before was closer to the solution. Okay, let me see. I'm kind of seeing other answers. Okay, all right. Okay, so I think I need to help you here. So loop is good. We're gonna get to a loop, but not right now. There's no loop in C, and we don't wanna think of a loop here. If there's no loop here, you will not have a loop here, like a branch on equal. Let me help you. Let me help you with the answer. What you want to put here is the value 9. That's what you want to put. Now, essentially what that means is you want to put a register here that contains the value 9. So you can say add immediate T009. If you do this, this one's going to put 9 in T0. And then when you do this, that's going to take the value of this, which is 9, and it's going to load it into the memory. Where exactly? At this location, 0 plus SP, which is exactly the location that we want to put the 9 in. So these two lines are going to put 9 at this location. Forget about a loop right now. We don't want to do it in a loop because in C, we're not doing it in a loop. We're just going to do it kind of by lines here. All right, does that make sense? If it doesn't, do you have questions? Okay, so Anthony's saying, how would the computer get the value 9? Well, when this gets translated to MIPS, so when we translate this code to MIPS, we have access to it. So so it's easy for the computer, for the compiler to be more specific, to look at this and convert it to this. There's nothing special here that we did. We didn't have to look here. We didn't have to know anything extra. So the compiler is going to look at this and it's going to say, oh, this is 12 bytes because we have 3 integers. So I'm going to allocate 12 bytes on the stack. And it'll say, okay, the first element is 9. So I'm going to put 9 in T0. And then I'm going to load word that T0, which contains 9, at SP, which I just kind of moved. And then I'm going to do it at the beginning of SP because I'd like the first element to be here. So it's really not that difficult for the compiler to do this. Okay, so let's do the second uh, load word. So here we'd like to put 3, And Grace proposed something that I like a lot, and it looks like this. Add immediate T003. So let's put the value 3 in T0, and then I'm going to load word T0, and then instead of having 0 here, Grace decided to put 4 here. And then we would put SP. And this is really perfect. This is exactly what we want. What's going to happen here is we're going to put 3 in T0. So we're going to overwrite the old value of T0 because we don't need it anymore. So instead of, so there's a few things that I like about this answer. One of them, instead of using T1, we're using T0, and that's because we don't need T0. So that was a smart decision. We don't want to keep using different registers. And then the other good decision was using 4 here, because we know that load word is going to add 4 to SP, and that's going to be the address that we're going to use. So SP right now is here, and if you add 4 to SP, you're going to end up here. And this is really the address that we want to use to put the value 3 in the RAM. So this is perfect. Now, sometimes students propose another solution. And the other solution looks like this. How about we move SP? So we say add immediate SP, SP4. So we move SP, and then we do something identical to what we did before. So instead of what Grace proposed, and that would be essentially, so what Grace proposed was to say, let's put 3 in T0 and let's do 4 here. This was the proposed solution. And sometimes students say, we can also do that. We can move the stack pointer by 4, and then we can put the value there. This would be very bad to the point where you would lose points on it in the exam. The reason why this is very bad is because you cannot move the stack pointer as you please. I mean, you could, in the sense that it's going to be syntactically correct, but it would be very bad. The reason why it would be very bad, because the stack pointer is the protector of your stack. So you think of it as a kind of a border. As soon as you move the stack pointer to another place, it's almost like you're telling everyone else that they're free to change anything below the stack pointer. But that's not the case. I mean, the whole point of this code is to kind of allocate 930. You don't want to allocate 9 and then allocate 3. And as you're allocating 3, you're going to lose the 9. So right now we're kind of talking about multiple kind of pieces of code running at the same time, but without kind of delving into unnecessary details, the stack pointer should always at all times be the protector of your stack. And the moment you move it, it's almost like you're telling everyone that, you know, they're free to change anything below the stack pointer. And you don't want that. You certainly do not want that. So this solution, while it will work in this case, it's a very bad solution. Again, to the point where I would consider it wrong if you answer it in the quiz or in the exam. So that's what we would do. Okay, do you guys have, does that make sense? Do you have any questions? Give me a thumbs up or thumbs down. Okay. All right, so what's the last one? The last one should probably be easier now that we did 2. Let me get rid of this. All right, give me the last one. Okay, so Anthony gave us this, add immediate T0, 0, 0, and then load word T0, 8, SP. That's perfect. Now, we probably could have removed this line. And why is that? We could have, we didn't need this line. Can someone tell me why? This line was not really needed. Yeah, exactly. We could have just used 0. So we can get rid of this and we can use 0 here. Okay. So just to recap, when this code executes, of course, right now, we're not talking about those. Those are still here. We're not talking about those. But when all of this executes, when we run it, let's say when we run it, it gets compiled to assembly, and then the assembly becomes machine code, and the machine code gets loaded to the RAM, into the RAM, and then we start executing instructions. These global variables and arrays, they're going to be here. This that you see here, this single line is going to become all of this. And the stack is actually going to be empty. So when you load everything into the RAM, the stack is going to be empty. So I'm going to do that. I'm going to say the stack is going to be empty. And the stack pointer is going to be outside of the stack, which is here. That's what's going to happen when you load your code into the RAM. So how many lines do we have? 1, 2, 3, 4, 5, 6. Each one of them is going to be a line. 1, 2, 3, 4, 5, and here we have 6. Let me copy and paste the stuff. Okay, we do that here. Of course, each instruction is 4 bytes. That's why each instruction is taking a row. Now, of course, those would be in zeros and ones. Those would be in machine code, but we haven't talked about converting this to machine code, so we're going to use MIPS. So this is what happens when everything is loaded into the RAM. And as we're executing one instruction at a time, we're essentially allocating space and putting values in the RAM, in the stack. Of course, it's in the RAM, but also it's in the stack to be more specific. So this would be the code section. This would be the static data. This would be the heap and the stack. We're going to only do the stack for now. And when you load your machine code into the RAM, it'll look like this. And the CPU is going to start fetching one instruction at a time, and it's going to execute those instructions. So when it fetches this one, and then when it executes it, oh, it's going to move the stack pointer by, oh, okay, I should have actually flipped them. Let me do that. All right, so yeah, so it's going to start fetching one instruction at a time from the bottom, going up. And this one, when it's executed, it's going to move the stack pointer by 12 bytes. It's going to go here. That's what's going to happen. And then when this one is executed, it's going to put 9 in T0. That's not going to really affect the RAM. When this one gets executed, we're going to put 9 here. So I'm going to merge all of that. And I'm going to put 9. That's what's happening when I execute this one. And when I execute this one, I'm going to put 3 in T0. That's not going to affect the RAM. When I execute this one, that's going to take all that space, which is really SP plus 4, and it's going to put 3 in it. And then this particular code is going to again, add 8 to SP. We're going to end up here, and we're going to put the value 0 here. All right. Do you have any questions about this? Okay. That looks, I mean, I'm happy. I think it doesn't seem that you have questions. Um, we don't have too much time. So because of that, we cannot cover a lot of new material. But what I think would be a good idea would be to show you how we convert this to assembly. So I actually showed you how you convert this to assembly, which is something that really you helped me with. You kind of knew this. All of that is syntax that you've seen before, but you were able to use it to accomplish what we need. So that was great. And now I want to show you how to do the syntax for this one, which is new. And this is going to be easy. So I think 10 minutes should be more than enough to do this. I'm going to stop the recording anyway because it's a different topic. So this one's going to be a long recording, and the next one would be very short, but that's okay. Let me stop recording.